Hi, this is Tom, and in today's video, what we're going to do is we're going to look at the motivation behind what's called L'Hopital's rule. And before we even do that, I need to do a warm-up. And the warm-up is this. It's recall that a curve can be locally estimated by its tangent line. For example, if I have just some curve, so let's draw our curve in this nice pretty melon color. If I just had some curve like this one, and then what I can do is my tangent line might be this point right here. So there's my tangent, and then it's going to come up like this. So here's my curve. Let's go back. This is my curve F, and this blue line here is the tangent line, and we're going to call it E, and I'm going to use a sub F to say that that's the approximation or the error line of x. We have f of x and E sub f of x, and what we also said then is that that's at the point, here's my x-axis, here's A. This creates the point of A comma f of A. And then what we did is we found that the approximation E sub f of x, of x is equal to, well, the slope of the line, that's f prime evaluated at A times x minus A plus f evaluated at A. And that was my approximation function. Okay, so we're going to need this. We're going to use that in a little bit. And let's take a look. So L'Hopital's rule says this. Let f and, I'll write it f and g. Let f of x and g of x be differentiable functions. And f of A is equal to 0, but that is also equal to g of A. Then what we can say is this. This is the amazing part. It says then the limit as x approaches A of f of x over g of x. And notice that right now this is just as x approaches A, that would be 0 over 0. That's an indeterminate form. But L'Hopital's rule says, well, if you take the derivative of both of those and then again apply the limit, so the limit as x approaches A, this time of f prime of x over g prime of x, the limit of the derivatives is the same as just the limit of the quotient of the function. So let's take a look. Let's take a look and see if we can see why that might be. So here we go. I'm going to draw two curves. Let's take a look. I'll do these in different colors so we can distinguish them. So I'm going to make a steep curve. I'm going to call this one we'll call that f of x. And then, so that's a nice pretty blue. And then we'll have a green curve. It'll look like this. And this is the curve g of x. Now, notice, and so they intersect in this melon-colored point right here. So this would be my x, my x-axis is right there. And notice that what L'Hopital's rule says is that they're both 0 at that point. So they both cross the x-axis at the same point. Now what we want is remember, we can estimate both of these curves, and I'll do that, is our approximation is pretty close. Let's come back over here to our approximation curve. And what I wanted to show you is, notice that if I had to approximate my curve here, just something a little bit above A, well, the blue line is pretty close to the reddish colored line. Or if I went just a little bit below, again, it's still pretty close. And so that's what we mean by locally. Like, not locally might be way out here, and you can see that the error is going to be pretty dramatic compared to if you were close to A. So in other words, what we want to do is, we don't care about these regions further out. All we care about here is just this little tiny local region of F and G. And so we're going to just take this. This is going to be like, like a window, like I can zoom in. And I'm going to draw that window. But here's the beauty, is in that window now, locally, we could think of f of x and g of x as lines. So let's do this. So here's that window. I'm blowing it up, making it nice and big. Big picture. Remember, this is being blown up many times. And so I get this. And then let's put we have our melon colored axis in here. And then I have my blue. But now, notice that the tangent line in here is I'm going to try to draw it, is about that steep, right there where it crosses the x-axis. And so this now is no longer f of x, it's f of x approximated by a straight line. So we're going to call it EF of x. And similarly, g of x, well, if we just look at that tangent line in that little window, which is our big window down here, notice that we have a picture straight line that looks like that. That's E, that's the g approximated by the straight line. We're going to call it EG of x. All right, now that we have that established, let's write these out. So I'm going to have to scroll up a bit. I'm going to scroll up, and let's write what we found. So here's what we found. Notice EF of x at A, and this is, I'm going to come back up here. Here's my point right there. That's the point A, comma, f of A. But remember, at f of A, it's 0, so really this is the point A, comma, 0. Okay, so I have EF of x. This is equal to f prime of A, x minus A, plus f of A. But now if we look back at our point, we know that f of A is 0, so I'm going to simplify this as f prime of A over x minus A. And for g, we'll write it again. For g, I get E sub g of x is equal to g prime at A, x minus A, plus g of A, and again g of A is 0, so this simplifies to g prime of A times x minus A. Now let's do this. So if we think of it this way, we could say, okay, well then the limit as x approaches A of f of x over g of x, well, that's just 0 over 0. But let's think of it this way. It's also the limit as x approaches A of EF because we're just looking right close around a. That's just e sub f of x over e sub g of x. Well, let's continue this out. If I do that, that's the same as we just write these in here. Well, this is the limit as x approaches a of f prime of a times x minus a over g prime of a x minus a. Oh my gosh. And look at this. I know some people don't think this is good mathematics to show what I'm going to cancel, but I like it. It's just kind of rewarding. So I'm going to cancel the x minus a factor and then look at what I have. There's my result. This is equal to the limit as x approaches a of f prime of a over g prime of a. Well, we've already evaluated these, so there's no limit to take. We're just left with f prime of a over g prime evaluated at a. So that's the intuition behind how L'Hopital's rule works. And let's just do one quick example with that. And that was this. Recall when we were finding the derivative. So I'll write this: the derivative with respect to x of sine of x. And this gave us this function. It gave us the function of sine of x over x was part of the derivation using the formal rule for the derivative. And we went through this long and difficult proof, and we had to use the squeeze theorem. But let's try this. Let's see now if we can find this limit more quickly. So the problem, and also remember when you're finding this in using the derivative formula, those x's are probably h's, but the variable doesn't matter. So let's try this. The limit as x approaches 0 of the sine of x over x. Well, right now this equals 0 over 0, which is indeterminate. That's what we call it, which is indeterminate. Indeterminate. So now, because we have the 0 over 0 form, we can apply, I'm going to write it that way. We can apply L'Hopital's rule. So I'm going to write that out. Let's take a look. We'll just write out all of the steps here. So we're going to take the limit as x approaches 0 of the sine of x over x. This is equal to the limit as x approaches 0 of, now we take the derivative with respect to x of the sine of x over the derivative with respect to x of x. Now notice this, and I'm going to put this in another color because it's pretty important, is this we are not using the quotient rule. This is not a quotient rule. It's very simply the derivative of the numerator divided by the derivative of the denominator. That's our result. So let's keep going. So in other words, this becomes the limit as x approaches 0 of the derivative of sine is the cosine of x. And the derivative of x is just 1. So when we take the limit, this is just becomes the cosine of 0 over 1, which is just 1 over 1, which is just 1. And that's how we can use L'Hopital's rule to do what was very difficult geometrically now is very simply with our applications of the derivative. Also, so L'Hopital's rule applies to the indeterminate forms. There's a few of them. And we'll actually, you know what we'll do? We'll take a look at those different indeterminate forms in our next video. Thanks for watching, and we'll see you in the next video.